on Wednesday doing molality and mole fractions. All right, molality, mole fractions. So we're going to take that same concept and move ahead a little bit and talk about mass percent, or percent by mass. All right, so another way of determining concentration of a solution is the percent of the one component compared to the mass of the entire solution. So if you've ever gone and bought hydrogen peroxide, it's 3% by mass hydrogen peroxide. Or last semester when you did the acetic acid titration lab, you figured out that acetic acid is, 10% by weight in water. Right, something like that. And so it's a common way of measuring consumer product concentrations. And so as this name implies, it is a percent that involves the mass of one component divided by the mass of all the components in the solution. So let's go ahead and do an example. Actually, I have 2 example problems today. Very exciting. Let's do the easy one first. All right, so let's say you have an alcohol-water mixture that you made by dissolving 46 grams of ethanol into 16.2 grams of water. I would like to know the mass percent of just the ethanol in the mixture. So using our mass percent equation, oh yeah, if you don't have your calculator out, go ahead and fish it out because we're going to need it. All right, so the mass of ethanol was given in the problem. How do we go about finding the total mass of the solution? Add them together. Good, just warming up. Good, good. So if we add them together, let's see, that total mass should come out to be 486.1 plus 116.2. So far, so good? Yeah. Times 100%. So 46.1 divided by 162.3 times 100. How many significant figures do I get to have in this problem? 3 total, which means how many decimal points do I get? 1. Good there, good warm-up problem. Some addition and division all in one. Oh, and multiplication all together. Good. Have you guys all done the worksheet in lab this week? Was that great? Yeah, super awesome. Just getting you ready for the semester. All kinds of awesome calculator tricks. Good, 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 good. All right, let's do a trickier problem. Doesn't have any natural logs in it. All right, so I have a solution that on the label says it's 85% phosphoric acid, and the label also gives me the density as 1.689 grams per cubic centimeter. But for the experiment I'm doing, I need to use, it's in molarity. So I have to figure out how to get from percent by mass to molarity. So in order to solve this kind of problem, we have to make a big assumption, which is not that big. But in order to solve this, we're going to make the assumption we're going to assume that we have 1 liter of it. So it's no different than some of the stuff you did in 108 with when we looked at masses, right? You assumed 100 grams of something. Same thing, we're going to assume 1 liter in this case. All right, so first question. I would like to know right, because I'm in percent by mass. So if I can figure out the mass of the entire solution, then I can figure out, well, 85% of that is this much mass. And if I know mass of phosphoric acid, I can get to moles of phosphoric acid. So I know I have a liter solution. What's the other thing I gave you in the problem to help you get to how much the solution weighs? Gave you density. Okay, so we have 1 liter. Which I didn't give you any significant figures on that. Assume an immense amount of significant figures. All right, so I had 1 liter, so I converted that to milliliters so I could use the density. And now I'm in grams. So if this has a ridiculous number of significant figures, how does this play in? Do I care about how many sig figs are in a conversion factor?
No.
No, we do not. We care about this. So it has 4 sig figs, so we get 4 sig figs in the final answer. I don't know, I'm using my calculator. All right, so I know that 1 liter of that weighs 1,689 grams. All right. Now I know that 85% of that mass is phosphoric acid. So I want to figure out if I know it's 85%, how do I use the whole mass in the 85%? So that should get us to 1, 4, 3, we'll round. So if I know the mass of the entire liter, from my problem I know 85% of that mass is phosphoric acid, so 85% of the whole thing should be that much. Then we're ready for the last step. So now I know grams of phosphoric acid. What is one thing I have not told you that you need in order to go from grams to molarity? Molar mass. Which you could easily figure out on your own, but I'm a generous person, so I'll go ahead and tell you. .99 grams per mole. What is the issue that I've now run into? Right, if I do this, I'm in moles, but I want to be molarity. So molarity is in moles per liter. Right, I gave you 1 liter. So you just have to remember that I gave you 1 liter up here. Good. And that should be 14.36. How do we feel about that? Fairly confident? That's like the trickiest problem I could give you with any of these things, be able to convert from one to another. Alright. In that case, let's talk a little bit about some other fascinating fun facts you can share with your friend over the 3-day weekend about solubility. These will be conversation starters, for sure. Conversation starters. So, let's talk about temperature and solubility. Right, we said, I think it must have been Wednesday, that solubility depends on temperature. Right, if you heat your solution up, more things dissolve in the solution. If you cooled off, less things dissolve. So when a solid is dissolved into a solution, you end up making an equilibrium. Right, where so much has dissolved and so much hasn't dissolved, you end up in that kind of equilibrium. If you increase the temperature, you will force a change in that equilibrium. Right, so if you heat it up, more can dissolve. So, what's a good example? So it all comes back to thermodynamics. So this process is going to be controlled by thermodynamics. So just as a quick review, all right, we have our two different ways that heat can flow. If it's exothermic, is it going out or is it coming into your system? Going out. So since there's only two options, the other one has to be the opposite. All right, which one of those two is the one that makes the experiment feel like it's getting hotter? Yep. So this one makes it feel like it's getting colder. Good there, all fairly coming back. Okay. So let's talk about how that relates. So that's true for solids. We don't often talk about just solids dissolving. We also have to look at how do gases get dissolved. How many people in here fish? How many people ice fish? Ice fish, where you sit out on your little, you drill a hole in the ice, you bring your ATV with the little shack over the hole, and you sit in the shack, and you just... I have done that. I obviously don't live in the climate that allows for that, but when I was living in Fargo, that was the thing to do. Everybody went ice fishing on the weekend, so we all hung out in these little shacks on these lakes. So, if you've ever been fishing, even in the colder, not really cold at all climate of Georgia, chillier climate, I don't know if you've ever thought, man, where are those fish at when the water freezes? No one's ever thought. Well, if you have thought about that, why do fish travel down to the bottom of the lake in the summer? Has everything to do with gas solubility, right? So fish breathe oxygen out of the water, and if temperature affects how much oxygen can be dissolved, well then you have to figure out where is the oxygen going to be when it's hot outside or when it's cold outside. All right, fish are pretty smart about that. Here's my fun story about this. So, my freshman year, there's a girl down the hall who had a goldfish in her room. right? Fair enough. You're allowed to have a goldfish as a pet. Well, our dorms got really cold in the winters. It was in Pennsylvania, so it was actually cold, not like here where it's tropical. So, right? And so she decided that her fish was cold. So she scooped out half the water, and she's put it in the microwave for 2 minutes. And then poured that water back in. Well, that fish half died. It was like this, and then for about a week, it laid on its side and kind of swum sideways. Eventually, it died. So what she had done is she had boiled the water, and that water had lost all of its oxygen. Right? She boiled all the oxygen out of it, so that fish was slowly suffocating in the tank because it had no oxygen to breathe. Above and beyond, like, it was kind of probably too warm for a goldfish, so it might have been like half boiled, half suffocated. So gas solubility makes a big difference to fish and to those people who drink soda. It's a big deal about gas solubility. All right, so warm water has very little oxygen dissolved in it. So if you're going out to a lake, you won't see any fish at the very edges of the water because the water's really warm. You won't see them, you'll see them in the middle where it's the deepest, so there should be the most oxygen dissolved. Or you'll see them in the shade, because in the shade, the water's cooler, so it should have more oxygen for them to breathe. You can also think about, I prefer my soda room temperature, which I know is really gross for most people, but I like room temperature because most of the bubbles have escaped. I don't like my soda real bubbly. And so if you drink room temperature soda, most of the carbonation will bubble out of it because it can't hold as much. If you drink a really, really, really cold soda, it is super, super bubbly. And it's because it's cold, so it's able to hold more carbon dioxide in it. There's your fun conversation starter for this weekend. Ask your friends how they like their soda, and then tell them about gas solubility. And that if they want more gas dissolved, colder. More bubbles, colder, less bubbles. Yeah, so. Let's see. So gases that dissolve to an appreciable extent, like carbon dioxide or oxygen, do so exothermically. Which means if we wrote out an equation for it, that if I dissolve my gas in water or whatever solvent you're choosing, you'll get a saturated solution of gas and heat gets released. All right, so exothermically we just said the heat flows out of the system into the surroundings. Well, that's what this is saying, exothermic. So, if that is going to be our equation, let's say you have a sample that you want to degas in some way. You want all the bubbles out of it. What could you do to force the gas out of the solution up into the air? Increase the temperature, right? So like in the case of the fish, she boiled the water, which forced all the water out of it, all the air out of it, and so there was nothing left for that fish to breathe. Plus, it was probably too hot for a goldfish. It was a sad thing. It was just like its tail sort of worked, and just kind of and did this, and then it could only lay on one side, like it couldn't flip over, and then eyes started to bulge out. It's a rough-looking fish. So, don't do that at home. That's my lesson. Don't do that at home. It's kind of like, what was that movie, Basic Instinct, where she boiled the rabbit? Similar to that. That's a really old movie, but yeah. All right, so add heat. Oh, to remove heat. That's not right. Add heat to remove gas. That answers that question. That's a terrible mark. All right. Good on gas solubility? Okay. So temperature can affect it, but we can also look at how pressure affects solubility of gases. So there is a mathematical equation that helps us determine how much gas can be dissolved in a liquid. And it is directly proportional to gas pressure. So Henry's law is this equation right here. Molar concentration in moles per liter is equal to Henry's law constant, which is a constant for each So each gas has its own constant. You can find it in a table of constants in your book. And then P is the pressure that's being applied to the solute at the time. So, scuba divers, a few. I'm petrified of the water. That's definitely not me. I don't like getting in. I'm afraid something's gonna be in there and eat me. So I'll sit on the sand, but I don't like getting in the water. So, solubility of gases is the concentration of gases in equilibrium when the substance is all in its gaseous state. So we have to be concerned about what happens if we change the pressure to those people who are underwater. Right, your lungs contain some known pressure. Right, so your lungs are constantly under pressure because they are being filled and unfilled as you're breathing. Right, so you can imagine as you're diving deeper in the water, the pressure has to increase on your body and on your lungs, right, because you have more water pressing on you. All right, then you can imagine the opposite, right? As you're swimming to the surface, the pressure will decrease. And looking at that equation we had before, if the pressure decreases, the molar concentration will increase of whatever gas you're looking at. Which means as the pressure is decreasing, all that carbon dioxide that was fully dissolved starts to come out of solution and starts to bubble. Right? So the same thing you can think about is soda, right? Soda is under pressure before you open it up. When you open it up and decrease the pressure, all the bubbles start shooting out. Same thing when you're deep sea diving. So if you start swimming up to the surface too quickly and don't let your body re-equilibrate, carbon dioxide starts to bubble in your veins and in your lungs, which is what's the bends. You ever hear about people getting the bends? It's because they swum too fast to the surface and gas started to bubble in their veins. As you can imagine, not good for your body. Your body doesn't like that. And some of those bubbles can cause real issues if you do it too quickly. It can result in death. So there's your other fun fact. You can now talk to people about deep sea swimming. If you've ever watched people free dive on YouTube videos, I I can't imagine doing that, where they swim down for 5 minutes, holding their breath, and then they swim back up. One guy recently died because he swam to the surface too quickly, and it got a bad case of the bends and ended up dying when he got to the surface. So, gas pressure, important. That's that. All right, let's do an example problem where we look at one of these. Let's say, which one's better? So using Henry's law, so this will be a typical problem that you see in your book or in the mastering, where they give you 2 of the 3 variables and you have to find the third. So our equation is this, right? We're given the concentration and we're given K. They're asking us to find P. Oh, I forgot my units. That should be mole. And this is so pretty straightforward, right? Just division. How many significant figures do I get to have in my final answer? 3. And then what will be the units of my pressure? Atmospheres. C, right? Okay. Feeling confident about pressure, gas, temperature? Okay. Okay, so let's look at the last section, because those are all, the last thing in this chapter is colligative properties, where colligative properties are any property of a solution that depends only on the number of solute particles per solvent, not what it's dissolved in. So they seem kind of funky at first, but when I explain what they are, be like, oh, well, that makes sense. So let's say I'm going to dissolve sodium chloride into water. Do you guys